Hello everybody, welcome to my first video demonstration for a math concept. I thought it would be fitting that the first one I demonstrate for you guys is the most proven theorem out there, the Pythagorean Theorem. This theorem has over 1,000 unique proofs that it is true. And probably most famously, there is a unique proof attributed to President James A. Garfield, obviously before he was assassinated. Now, Pythagorean Theorem probably sounds very familiar to all of you. It would not surprise me if you could even recite it, remember it from your school days, and I still wouldn't be surprised if the grand majority of you would know how to apply it appropriately. However, I would be surprised if most of you could tell me why it's true, or where it comes from, or how we know that it is true. And so that's what I'm going to do today. Now, to do that, I'm going to choose one of my favorite ways of proving it, which does involve geometry. And so to do that appropriately, we're going to have to review two key geometry concepts, the first one being the area of a shape, and the second one being the angles of a triangle. Now, before we do either of those, though, we need to remember, how does the Pythagorean theorem apply? And what I have drawn here is a right triangle. A right triangle is a triangle, a three-sided polygon, that has a right angle in it, which I've denoted with this little box in the corner. Now, by convention, we label the sides of a right triangle, the shortest side A, the middle side B, and the longest side C. And if you remember your triangle inequalities, you know that the longest side is always going to be opposite the right angle. So here's my right angle. The opposite side is C. We give it a nice funny Greek name, the hypotenuse, and we call A and B the legs of the right triangle. So now, we're going to get into how do we find area. Okay, to find area, we start by defining measurement. So first, we measure in one dimension, along a straight line. So here I've drawn a line segment, I've given it two endpoints, and I've said that I want this length to be 1 unit. Now that unit could be anything. In today's terms, we may call it an inch, or a foot, or a mile, or a meter, or a centimeter, something like that, but we give it a name. And I'm just going to use the name unit, just a nice generic name. And then if I want to measure any straight length, like along any of these sides that I have for my shapes, I would measure how many of these would fit along those segments. For measuring the space inside of a shape, I'm now measuring in 2 dimensions. And so I need to create a 2-dimensional shape based on my unit. Now, we separate dimensions with 90-degree angles, perpendicular lines, right angles. And so I want to create a shape using only right angles. And so to do that, I start by saying, okay, well, I've got 2 endpoints. I'm going to go ahead and make a right angle here and make this side 1 unit. I'm going to make a right angle here and make this side 1 unit. And then I just need to make a right angle here and a right angle here, and what we'll find is that they're going to connect up, and that this length will also be 1 unit, and we have a square. But more importantly, we have a square whose area we define as 1 unit squared, or 1 square unit. And this is the base measurement for area. So my question becomes, how many of these squares will fit inside of this shape? Or inside of this shape, or inside of this shape, and that is the area of that respective shape. So to do that, it's also very easy. Again, I start by measuring the side lengths using the same original line segment measurement that I had here. So I could measure along here and say, okay, there's 1 unit and there's 2 units. Okay, so this side length is 2 units long. And then I could measure along here and say, oh, this side length is also 2 units, oh, and this one's 2 units, oh, and this one's 2 units. I've taken the time to measure all of that. And these are all right angles. I've made a square here. And so then I can say, all right, why don't I divide this up based on the number of squares that would fit in here, and then just count them. Oh, there's 1, 2, 3, 4. So the area of this square is 4 units squared. Now that's nice and easy. But at the same time, what if this were a ginormous square? I don't want to take the time to count all of those. How do I count them up faster? Well, if you remember your elementary school mathematics, you were taught that whenever anything's in a grid, all you need to know is the number of columns and the number of rows and multiply them. And that's how many squares you got inside. Well, here I've got 2 columns and 2 rows, which just happens to be my length and my width. And since all of these are the same, we sometimes refer to these as just side, or a generic one would be S. And so I'm saying what I'm really doing is just 2 times 2, which is 4. Or for any given square, I can say that, oh, it's easy enough to find the area of a square. So I say the area of a square, we use an S to show I'm talking about a square, is just the side length times itself, which mathematically we write with an exponent of 2. Okay, that's pretty easy. All right, moving on to this shape right here, I've purposely drawn a rectangle from the German recht, meaning right angles. These are 4 right angles, so I've got a rectangle. And a necessary consequence of a rectangle is that these opposite sides are the same length. But now not all 4 sides are the same, so we have to have a slightly different approach to the area. Well, again, I can start by thinking of a grid. Okay. Well, if again this is 2 units across, I could say, well, then I can start dividing things this way. And then if I want to measure how many units down, I've got 1, 2, 3, 4, 5. Not perfect, but they're there anyway. So I could say it's 5 units down. And so then I start drawing my grid across here. And then I can say, okay, well, this is also 2 units. This is 5 units. And I can count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But again, I don't want to always count. I'd like a nice formula, a faster or shortcut to finding the area for any sized rectangle. And so I think back to my elementary school math again. It's just a grid. I know the number of columns 2 and the number of rows 5, and I can just multiply. And with rectangles, we don't say side squared because they're not the same sides. We say length and width. And so our formula for a rectangle, I use R for rectangle, is just length times width. And we use a cursive L because otherwise a script L may look, or not script, a print L may look more like a 1. All right, and so here I've got 2 times 5, and that's 10, which of course gives us the number we counted. Nice and simple, very easy. And finally, we're going to talk about a right triangle. How do we find the area of that? Well, without me starting to draw, I think it should be pretty obvious I can't. I can't sit here and try to draw the number of these unit squares inside of here that is going to give me the accurate area of this triangle, so I need another tactic here. Well, I am going to go back to this, and I'm going to label some sides again here. So thinking back to my original right triangle, that's A, and that's B. Okay? And those make the right angle, which we saw was very important for the rectangle and for the square. So I know they've got to be important for the right triangle. Ah, you know what? I'm going to pretend there's something more to this triangle. What if I were to extend this side at a right angle and this side at a right angle? What would that give me? Think about the larger shape here. Well, if I've got 4 right angles, I've got a rectangle, and so I know the opposite sides of rectangles are the same. And what I've really got are 2 congruent right triangles just rotated and placed next to each other. And if they're congruent, they're the same, and so their area is the same. That means if I know the area of this full rectangle, I could just cut it in half along the diagonal, and I've got the area of one of the triangles. Well, what's the area of the full rectangle? It's length times width. It's A times B. That's the full rectangle, but I only want half of it for that triangle. And so I've got the area of my right triangle. Here I'm going to designate that because I'm not talking about triangles in general, just the right triangle. Well, that's just, we said the area of the rectangle, A times B, but then cut it in half. And these are going to be the formulas that we need for the area portion of our proof. Now we're going to review something about the relationship of the 3 angles of any triangle. And what I love about this one is it's just as easy to demonstrate this for all triangles and not just for right triangles. Separate from the area one, I left out any other non-right triangle, but that's okay, we don't need it for this proof. All right? So here I've drawn a generic triangle, And so, just as in the name implies, try three angles. There's three angles. And by convention, we use Greek letters to label them. Angle alpha, angle beta, and angle gamma. And we're going to show how these three angles are related to each other. So to do that, we start first by taking one of the sides. Here I'm going to choose the bottom one and extending it like a line that goes forever in both directions. And then I think about drawing a parallel line, a line that will never intersect this line, such that it intersects the opposite point on this triangle. So my parallel line will look something like this, where it does intersect the triangle right at that point where angle beta is. All right? Now, to see what we're going to do here, we're going to start by only picturing one of the remaining sides of the triangle. So temporarily, I'm going to be removing this side, and I'm just going to erase this notation. But we remember angle beta is there. All right? And I'm going to focus first on angle alpha. Now, this side intersects both of these parallel lines, and we call that a transversal. So again, I will show kind of what that looks like if I were to extend it. And something that we accept as a postulate of geometry is something called corresponding angles. Now take a look first, right here. I have got these two lines intersecting, creating four angles. The top left, the top right, the bottom left, and the bottom right. And it's a straight line, and as it comes up here, it's going to intersect a parallel line, creating four unique angles. Top left, top right, bottom left, and bottom right. And we say corresponding angles are two angles that are in the same position in this kind of a setup. So if I think here top right and think here top right, those are corresponding angles. And as these lines are parallel, we say then these two angles must be the same measurement. Therefore, that is also angle alpha. It has the exact same measurement. All right? Now, what we want to think about is, what if I were to think about this line as being an angle by itself? So picture this. I start here and I've made angle alpha, and then I rotate until I make a nice straight line. Now we know that a right angle is 90 degrees. And if I were to think about putting two right angles together, I know that what remains on the bottom must be 180 degrees. It's 90 plus 90. And so I can kind of think about removing this middle piece, and I've got 180 degrees, or a straight angle. Well, that's really what we've got going right here. This is a straight angle. And this portion of the angle is alpha, which tells me that this entire thing being 180 degrees, this remaining piece here must be what's left over. In other words, this must be 180 degrees minus angle alpha. All right? Using that same logic, I see right here I've got a straight angle again. And if I know that this piece is 180 minus alpha, this entire thing is 180 degrees, then this remaining piece must be the leftovers. Or, to put it more accurately, this piece must be 180 minus what I started with, which was 180 minus alpha. Now that's really ugly, so let's clean it up. All right, if you remember your distribution from algebra, I've got a negative out front. I distribute the negative inside to both terms, leaving me with 180 minus 180 plus, because a negative times a negative is positive, alpha. 180 minus 180 is 0, so it just cancels out, leaving me just with alpha. Meaning this angle right here measures alpha. Okay, now I've redrawn that third side we were ignoring. And what we're going to do is we're going to basically do the exact same thing with this side that we just did with this side. I chose this one arbitrarily. It didn't matter which one I start with. So the process is going to be the exact same. But for this purpose, just to make it easier, I'm not going to bother erasing this side. We're going to go ahead and use our imagination and kind of ignore it while we do this. So again, this is a transversal. this side can be extended and thought of as intersecting two parallel lines. Thinking again about corresponding angles, my top left is gamma, which means that here my top left must also be gamma. If I mark gamma with 2 arcs, then I know that this was the worst gamma I've ever written. There we go, a little better. And I've got that angle must be gamma as well. And again, using my logic of straight angles, I know from here to here must be 180 degrees. So I know that this distance must be what's left over, which must be 180 minus gamma. And then again, using the exact same logic, I know this distance is 180 degrees. And so I know since this is 180 minus gamma, this must be what's left over. So this distance must be 180 minus what I already have, which is 180 minus gamma. And doing the exact same algebra, which I'll just do again for reminder's sake, distribute the negative. 180 minus 180 plus gamma. The 180 minus 180 is 0, so it cancels out, leaving me with gamma. And so now I know this must also equal gamma. Finally, we return beta back to its original spot there. And let's take a look at what we have. We started with a triangle with 3 angles, alpha, beta, gamma. And I've drawn a picture where I have moved alpha and gamma, alpha up to here, gamma up to here. And I've shown that they must be the exact same measurement. So now I'm only going to focus on right here, alpha, beta, and gamma. Well, take a look. Alpha, beta, and gamma, they all make a straight angle, which means they have to add up to 180 degrees, which means I can state the following. In any triangle, the 3 angles, alpha plus beta plus gamma, must equal 180 degrees. And that's true for any triangle. Now, to apply what we just learned to a right triangle. And remember, a right triangle has to have a 90-degree angle here, all right? Which means we've got 2 angles remaining. So I'm going to label them the way we normally do, which is that the angle opposite the shortest side will be the shortest angle. So if A is my shortest side, this is my shortest angle, I'll call it alpha. And the angle opposite my middle side, which is B, I'm going to call that beta, which means that the angle opposite my longest side, C, would technically be gamma. Although I don't really care too much that it's gamma, I'll go ahead and put that there, which turns out to be my 90-degree angle. Why does the 90-degree angle have to be the longest side? Well, let's plug that into this equation right here. I have alpha plus beta plus gamma equals 180. We know gamma is 90, so now this gives me alpha plus beta plus 90 equals 180. And then I subtract 90 from both sides. Alpha plus beta equals 90 degrees. Therefore, in a right triangle, when I have a right angle, my remaining 2 angles have to sum to 90 degrees, which means they can't be 90 degrees or greater themselves, so they have to be less than 90 degrees, which we call acute. So I know that in any right triangle, the right angle has to be the largest angle. And then I label the other 2 alpha and beta. Now I don't know, without doing trigonometry, the measurements of alpha and beta, but I don't care. What I care about is that their sum has to be 90 degrees. And now we're going to put all of this together in my favorite proof of the Pythagorean theorem. And now we come to the part where we're going to actually prove the Pythagorean theorem. And to do this, I've started with a right triangle. Let's take a look at this one right here, with sides A, B, and C. And I've copied it 4 times, and I've rotated each copy and placed them in such a way that they all kind of overlap a little bit, or their sides touch each other. And by doing so, I've also created 2 other shapes as a consequence. There's this larger outer 4-sided shape, which we see right away all 4 sides are the same. They're all C, so we know it's at least a rhombus. And then I've also created this inner 4-sided shape. And to do the proof, what we're going to do is we're going to find the area of this entire shape two different ways. First, we think of it as one shape, find its area. Then we find the area of all 5 inner shapes and add them up. And then we know they have to be equal, so we'll set them equal to each other and see what mathematically happens. All right, first we need to know something more about this outer shape here. Well, I need to look at the angles next. I know the side lengths are the same, but what can I say about the angles? Well, let's go back to how we label our angles. So across from A is alpha, and across from B is beta. Across from A is alpha, and across from B is beta. Again, alpha, beta, alpha, and beta. And what we should notice is that in each corner of this 4-sided shape, I have an angle that is composed of alpha and beta, alpha and beta, alpha and beta, alpha and beta. And what we just got done showing was that in any right triangle, the other 2 angles, alpha plus beta, have to add up to 90 degrees. And since these are all congruent right triangles, then these alphas and betas are all the same. That's why I got to use the same letters. And so I know that alpha plus beta is 90, so I have a right angle here, a right angle here, a right angle here, and a right angle here. I have a square. So I've created a square using 4 congruent right triangles, which means I can find the area of this entire shape by using my formula for the area of a square, which is just side length squared. And a side length is c, so it's just c squared. And that's the first way we find the area. Now I need to focus on the area of each of these inner 5 shapes. And I'm going to start with this inner shape here because I don't know what it is yet. I just know it's 4-sided. It's a quadrilateral. Well, looking a little more closely, if I think from here to here is B, and from here to here is A, this is a portion of B, then from here to here must be the leftovers. What remains of B after I put on A, which is B minus A. Okay. And as I look here, I got the same thing. This is B, this portion of B is A, so this remaining piece must be B minus A. And of course, the same thing here. This is B, this portion is A, so the remainder must be B minus A. And finally, this last one, by the exact same logic, must also be B minus A. So again, I've created a rhombus, but I need to say something about the angles. Well, let's take a look here. This is a straight line, which means it's a straight angle. This is a 90-degree angle, which means the other piece must be what adds up to 180, but we know that 90 plus 90 is 180, so that means this is a right angle. And again here, a straight angle. I have 90 degrees of the straight angle. The remaining degrees must also be 90. I've got a right angle. And by the same logic, I've got a right angle here, and I've got a right angle here. In other words, I've created a square in the middle as well. So to find the area of the square in here is also very easy. So I'll start with that. That's just the same as what we did for the outer circle. So it's just the side length, which is B minus A, squared. Well, that's nice. Okay. But that's not all, because I still have to add on the areas of each of the triangles. So I'm not done, but that's how I started. Now I look at each of these triangles and I think, okay, how do I find the area of a right triangle again? Well, I look at the right angle and I take, as if it were a rectangle, I take the length times the width, which is A times B, but then I cut it in half because it's not a full rectangle, it's exactly half of a rectangle. So each triangle is 1/2 A times B. And each triangle is the exact same. So I could add 1/2 A times B 4 times, or I could just multiply by 4. And there is where I have 2 different ways of calculating the area of this shape. Now, it's a little kind of messy there. It looks like I'm saying 4.5 AB, and it's not. It's 4 times 1/2 times AB. So I'm going to clean that up a bit. And 4 times 1/2, well, that's just half of 4. That's just 2. So what I'm really saying is this second way is really, this second way is really B minus A, the quantity squared, plus 2AB. Finally, we're going to equate the two and see what happens. Okay, so we've got the area of that shape can be calculated either as C squared or as B minus A squared plus 2AB, but that they're the exact same, and so I just set those two things equal to each other. Now, to do a little bit of algebra to simplify, we're going to focus first here on this quantity being squared. Now, some of you might think, hey, I can just use a formula for that, but I don't remember what that formula is. I don't care. I don't like to memorize formulas. I think that's silly, and I think it defeats the purpose. So instead, we're going to work it out. How do we expand this mathematically? Well, we know that a squared means I'm multiplying it with itself. So, on my next line here, I'll write C squared equals B minus A times itself, B minus A, and then don't forget to bring down the leftovers, which is the plus 2AB. Okay? And what I'm doing is I'm distributing each term in the first quantity with each term in the second quantity. And so I like to do that in an orderly way. You may have remembered something called FOIL, first inside, outside, last, or first outside, inside, last. I can't even spell. This is not a spelling channel. And so we're going to kind of follow that, but that's not what I want you to memorize. Just use logic. So I'm just going to start with the first one here and multiply it with the first one here. That's B times B, which is just B squared. I then continue with this first one and multiply it with the second one, which is a negative A. Don't forget that negative counts. So it's B times a negative A, which is just minus AB. We like to be alphabetical in math. So there's a little bit of spelling, I guess. And now I want to do the same thing. I've multiplied my first term with everybody here, so I'm going to do the same thing with my second term. My negative A times the first term in the second one, which is also minus AB. And then my negative A times my negative A. Oh, well, a negative times a negative is a positive, so it's plus A squared. And then, of course, bring down the leftovers, plus 2AB. And we still want to clean this up a little bit. Notice how I've got the same terms here. I've got a minus AB and a minus AB. I have two of them. So what I really have is C squared, I guess I'll underline them there, equals B squared minus two of them, minus 2ABs. And then let's bring down my leftovers, plus A squared plus 2AB. And then hopefully you're seeing where we're going with this. I've got take away 2AB and add 2AB. Just as when we did with angles, we had a plus 180 and a minus 180. These two things are opposites. They just cancel out. They just equal 0. And what I'm left with is this B squared and this A squared. And again, I like to be alphabetical. And so I can rearrange this as C squared equals A squared plus B squared. And that is the Pythagorean theorem. And remember, it applies to right triangles. And so to see this in action, I need to have a right triangle in which I've got my right angle here. Here is A, my short side, B, my middle side, and C, my long side, my hypotenuse. And because I did not put any qualifications on this right triangle, I said it's just a right triangle set up in this way, reviewing area and angles of triangles, I've been able to show that for all right triangles, it must be true that the sum of the squares of the legs, A squared plus B squared, has to be the exact same as the square of the hypotenuse, C squared. And there you have it, the Pythagorean theorem. And remember, you watched it, you can't unwatch it.